What if I told you that nearly all the light in the universe is completely invisible to your eyes? That's right, 95% of the cosmic light show is happening right now, just beyond the limits of human vision. We gaze up at the night sky, thinking we're seeing the universe as it truly is, but in reality, we're only catching a tiny sliver of the story. The rest is hidden in wavelengths our eyes can't detect. Infrared heat signatures from newborn stars, ultraviolet rays blazing from distant galaxies, X-rays screaming out of black holes, and radio whispers from the dawn of time. This is the invisible spectrum, and it holds the keys to unlocking the universe's greatest secrets. Think about it like this: reading a book with 95% of the pages torn out. You'd miss the plot twists, the character arcs, the entire meaning of the story. That's exactly what happens when we rely solely on visible light to understand the cosmos. The invisible spectrum fills in those missing chapters, revealing celestial phenomena we never knew existed. It shows us where stars are born in dense clouds of gas, how supermassive black holes devour matter, and even lets us peer back in time to witness the faint glow of the early universe. Without it, we'd be blind to the most dramatic, awe-inspiring events shaping our reality. So how do we uncover these hidden layers of light? That's where the magic of modern astronomy comes in. Scientists have built telescopes that act like cosmic translators, converting invisible wavelengths into images we can see and understand. These tools have transformed the way we explore space, turning the universe from a silent movie into a full-color, high-definition epic. In this video, we're going to journey beyond the rainbow into the realms of infrared, ultraviolet, X-rays, and more. You'll discover how each type of invisible light reveals a different piece of the puzzle, and by the end, you'll never look at the night sky the same way again. The universe is far stranger, more violent, and more beautiful than we ever imagined. And the best part, we're just getting started. Picture the electromagnetic spectrum as the universe's grand alphabet, a collection of invisible letters that, when pieced together, spell out the story of everything. Just like how the same 26 letters can form a child's bedtime story or an epic poem, these wavelengths reveal everything from the gentle hum of distant galaxies to the explosive final moments of dying stars. But unlike human language, this cosmic alphabet isn't limited to what our eyes can read. It stretches far beyond the familiar rainbow of visible light, into realms we can only perceive with the help of cutting-edge technology. At one end of this spectrum, you'll find radio waves, long, lazy ripples of energy that glide through space undisturbed, carrying whispers from the earliest moments of the universe. These are the waves that let us tune into the afterglow of the Big Bang itself. Then come microwaves, famous for heating leftovers, but also for mapping the faint wrinkles in the fabric of spacetime. Next is infrared light, the warmth you feel on your skin from a campfire, which in space acts like night vision goggles, piercing through cosmic dust to reveal newborn stars still wrapped in their stellar cribs. Visible light, the narrow band we're built to see, is just a sliver in this vast spectrum, like a single chapter in an encyclopedia. Beyond it lies ultraviolet, the same light that gives you sunburn but also exposes the searing atmospheres of distant stars. Then come X-rays, the high-energy fingerprints of black holes and superheated gas, followed by gamma rays, the universe's most violent outbursts, signaling the deaths of massive stars and collisions of neutron stars. What's fascinating is how each type of light interacts with matter in its own way. Radio waves slip through walls, while X-rays penetrate flesh but bounce off bones. In space, these differences become our greatest tools. Dust clouds that block visible light, infrared slips right through, the invisible jets screaming from a black hole. X-rays light them up like neon signs. By learning to read this hidden language, astronomers don't just see the universe, they decode its deepest secrets. And speaking of secrets, few things remain more mysterious or more breathtaking than the stellar nurseries hidden behind thick veils of cosmic dust. That's where infrared light becomes our guide, peeling back the curtain on places where stars are born. Imagine walking into a room where the lights are off, but you've got a thermal camera. Suddenly, you see everything. That's the power of infrared astronomy. It shows us the universe's hidden warmth, the cradles of creation tucked away in the dark. Deep in the heart of the Eagle Nebula, a cosmic masterpiece hides behind thick curtains of dust until infrared light pulls them aside. The pillars of creation, immortalized by Hubble's iconic visible light image, look entirely different through the James Webb Space Telescope's infrared eyes. Where Hubble saw towering columns of gas silhouetted against starlight, Webb reveals a hidden fireworks display, countless young stars blazing inside those pillars, their heat punching through the dust like headlights through fog. This is the magic of infrared astronomy. It doesn't just show us what's out there, it exposes what's alive out there. Every speck of interstellar dust that blocks our view in visible light glows with warmth in infrared, turning obstacles into beacons. Protostars, still wrapped in their dusty cocoons, betray their locations with heat signatures long before they ignite nuclear fusion. Planetary systems still under construction, swirling disks of gas and debris, glow faintly in these wavelengths, offering snapshots of solar systems like ours in their infancy. Even entire galaxies, shrouded by cosmic dust billions of years ago, suddenly pop into view when we switch to infrared. Some of these galaxies are so ancient, their light has stretched into infrared over time, giving us front row seats to the universe's toddler years. But infrared's greatest gift might be its ability to freeze time. When Webb peers at distant galaxies, it's not just seeing through dust, it's seeing through time itself. The light from those galaxies spent eons traveling to us, meaning we're witnessing them as they were when the universe was young. Infrared telescopes have spotted galaxies so massive and mature in the early cosmos that they're rewriting our theories of how galaxies form. These discoveries aren't just filling gaps in our knowledge, they're tearing up the old playbook and forcing us to rethink cosmic evolution. Now, shift your gaze to the opposite end of the spectrum, where infrared's gentle warmth gives way to ultraviolet's searing glare. If infrared shows us the universe's hidden nurseries, ultraviolet exposes its firestorms. Massive stars, dozens of times heavier than our sun, burn so hot they flood space with ultraviolet radiation, ionizing gas clouds and sculpting nebulas like cosmic sculptors. The same UV light that tans your skin at the beach, out in space, it's the signature of stellar titans living fast and dying young. These stars don't just shine in ultraviolet, they dominate it, turning their surroundings into glowing landscapes visible only to telescopes tuned to these blistering wavelengths. And here's the twist, ultraviolet light doesn't just reveal stars, it betrays their deaths. When massive stars exhaust their fuel and explode as supernovas, they flood their surroundings with UV radiation, creating temporary beacons that astronomers use to map the universe's expansion. Even the hottest gas between galaxies, invisible in other wavelengths, fluoresces in ultraviolet, tracing a hidden web of matter that binds the cosmos together. From stellar birth cries in infrared to death throes in ultraviolet, the invisible spectrum tells a story far richer than our eyes could ever see. Massive stars live life in the ultraviolet fast lane, blazing so fiercely they rewrite the rules of cosmic visibility. While our sun bathes the solar system in gentle yellow light, these stellar behemoths crank their surface temperatures past 50,000 degrees, flooding space with ultraviolet radiation that would fry any nearby planets. This isn't just light, it's a full-blown cosmic blowtorch, ionizing the surrounding gas clouds until they glow like neon signs across the galaxy. The Tarantula Nebula, a star-forming frenzy in our galactic backyard, shows this drama in action. Hubble's ultraviolet eye revealed thousands of these young, hyperactive stars crammed together, their UV radiation sculpting the nebula into surreal shapes. Bubbles blown by stellar winds, tendrils of gas stretched thin by radiation pressure. It's like watching a celestial sculptor at work with ultraviolet light as the chisel. But UV astronomy doesn't just showcase stellar artistry, it tracks the life cycles of stars too wild for visible light to capture. When these massive stars rev up their fusion engines, they don't just shine, they erupt, hurling out material in supersonic stellar winds. Ultraviolet telescopes catch these gusts in real time, measuring how much mass these stars shed before their inevitable fiery finales. And what finales they are! A star that spends its life drenching space in UV light doesn't fade quietly. It either explodes as a supernova or collapses into a black hole, both events so violent they send shockwaves through the cosmos. Which brings us to the ultimate cosmic fingerprints of destruction, X-rays. When those UV bright stars meet their end, they don't just vanish, they leave behind scars in the fabric of space. Supernova remnants glow in X-rays as expanding shockwaves heat gas to millions of degrees. Black holes, the densest objects in existence, rip matter apart so violently the resulting friction emits X-ray screams detectable across the universe. Even colliding neutron stars, city-sized stars so dense a teaspoon of their material weighs 1 billion tons, unleash X-ray bursts bright enough to outshine entire galaxies for seconds. If ultraviolet light shows us the universe's fireworks, X-rays reveal the shrapnel left behind. Take the Crab Nebula, the wreckage of a supernova witnessed on Earth in the year 1054. To our eyes, it's a wispy cloud, but through an X-ray telescope, it's a frenetic particle accelerator with magnetic fields whipping electrons to nearly light speed, creating a pulsar at its heart that beams X-rays like a cosmic lighthouse. This is the hidden heartbeat of the universe, a rhythm tapped out not in visible light, but in wavelengths that expose the most extreme physics imaginable. And just like that, we've crossed another threshold on the electromagnetic spectrum, from ultraviolet's searing glow to X-rays cutting clarity, each revealing layers of cosmic truth invisible to the naked eye. The Chandra X-ray Observatory captures a cosmic battlefield where shock waves from an ancient supernova glow like ghostly halos, painting the aftermath of a star's self-destruction in eerie X-ray light. These aren't just remnants, they're particle accelerators on a galactic scale, where magnetic fields whip electrons to nearly the speed of light, creating high-energy radiation that visible light could never reveal. The Crab Nebula's pulsar, spinning 30 times per second, acts like a celestial dynamo, its X-ray beams slicing through space like a lighthouse from hell. This is the universe's high-energy frontier, where matter doesn't just behave strangely, it screams its presence in X-rays. Black holes take this violence to another level. As gas spirals into their gravitational clutches, friction heats it to millions of degrees, emitting X-rays so intense they outshine entire galaxies. The supermassive black hole at the heart of the Milky Way, normally invisible, betrays its presence through these X-ray tantrums, flares that spike when it shreds passing stars or swallows gas clouds. But the real surprises came when Chandra discovered quasars, galaxies so bright in X-rays they're visible across the universe. They're secret, supermassive black holes feasting on gargantuan amounts of material, turning entire galaxies into cosmic beacons. Then there's the X-ray background, a faint glow pervading all space, once a mystery but now recognized as the combined whispers of millions of black holes and hot gas clouds from across cosmic time. It's proof that what looks like empty darkness to our eyes is actually a seething, high-energy arena. Now crank the energy dial even higher past X-rays to gamma rays, the universe's most violent light. These aren't just photons, they're bullets of pure energy, born from the most cataclysmic events imaginable. When neutron stars collide or massive stars collapse, they unleash gamma-ray bursts so powerful they briefly outshine every star in the universe combined. The Fermi Gamma Ray Space Telescope catches these cosmic explosions, some so distant their light has traveled for billions of years before reaching us. Each flash is a death cry of a star, a message written in the universe's most extreme language. What's astonishing is how these gamma-ray bursts serve as cosmic measuring tapes. By analyzing their light, astronomers have mapped the expansion rate of the universe and even probed the structure of spacetime itself. The invisible spectrum doesn't just show us the universe's violence, it turns that violence into a tool for discovery. From X-ray whispers to gamma-ray screams, these wavelengths reveal a cosmos far more dynamic and chaotic than our eyes could ever perceive. On September 14, 2008, the Fermi Gamma Ray Space Telescope caught a flash of light so powerful it outshone the entire Milky Way for 2 seconds. This gamma-ray burst, labeled GRB 080914b, had traveled 7.3 billion years to reach us, making it one of the most distant and violent events ever recorded. When astronomers traced its origin, they found the aftermath of a collapsing star turning into a black hole. Its death throes unleashing enough energy to outshine 1 million galaxies combined. This isn't just a star dying. It's a star-going supernova on steroids, its core collapsing into a singularity while jets of plasma scream outward at nearly light speed, radiating gamma rays like cosmic distress signals. These bursts are nature's ultimate fireworks, but they're also cosmic alchemists. The same inferno that creates a black hole also forges heavy elements like gold, platinum, and uranium. When neutron stars collide another gamma-ray trigger, they spew out neutron-rich material that rapidly assembles into these precious metals, the gold in your jewelry. It was likely born in a cataclysm like this, ejected into space before our solar system even existed. Yet gamma rays aren't just about destruction. They might hold clues to one of astronomy's biggest mysteries, dark matter. Some theories suggest dark matter particles, when they collide, could annihilate each other and produce gamma rays. Telescopes like Fermi scan the sky for unexplained gamma ray excesses, particularly from dwarf galaxies packed with dark matter. While the evidence isn't definitive yet, every unusual gamma ray flicker could be a breadcrumb leading us to the invisible 85% of the universe's matter. Now flip the script from gamma rays' blistering fury to radio waves' quiet hum. If gamma rays are the universe's screams, radio waves are its whispered secrets. Cold hydrogen gas, the raw material for star formation, emits a faint radio signal at 21 centimeters, a wavelength so predictable it's become a cosmic yardstick. Radio telescopes like ALMA in Chile catch these whispers, mapping the distribution of gas between stars and even revealing the spiral arms of distant galaxies. But radio astronomy's crown jewel might be the cosmic microwave background, the afterglow of the Big Bang. This faint radio static, discovered by accident in 1965, shows the universe as it was 380,000 years after its birth, a baby picture of cosmic structure. And just last year, radio telescopes detected the faintest radio waves yet from some of the earliest stars, their signals stretched and diluted by 13 billion years of cosmic expansion. From gamma rays' explosive births to radio waves' ancient echoes, the invisible spectrum isn't just showing us the universe, it's telling us its life story, one wavelength at a time. Radio telescopes turn the cold, dark voids of space into symphonies of hidden activity. While optical telescopes show us the universe's glittering surface, radio dishes like ALMA, the Atacama Large Millimeter Array, tune into the whispers between the stars. Perched high in Chile's deserts, ALMA 66 antennas work like a single giant ear, listening to the faint radio hum of molecular clouds. These aren't just empty spaces, they're stellar nurseries so cold they're invisible in other wavelengths, yet brimming with the raw ingredients for new stars and planets. The same way a doctor might use an ultrasound to see inside the body, radio astronomers use these signals to peer into the densest, darkest pockets of the cosmos, places where gravity is quietly knitting together the next generation of stars. One of radio astronomy's most powerful tools is the 21-centimeter line, a signature wavelength emitted by cold hydrogen atoms drifting through space. It's like a cosmic barcode revealing where hydrogen gas, the universe's most abundant element, is clustering into galaxies or stretching into vast filaments between them. This faint signal has mapped the Milky Way's spiral arms, traced the flow of intergalactic rivers, and even hinted at the unseen tug of dark matter. Without it, we'd be blind to the universe's skeleton, the hidden scaffolding that shapes everything we see. Then there are pulsars, nature's most precise timekeepers. Discovered by accident in 1967, these rapidly spinning neutron stars beam radio waves like lighthouse beams, sweeping past Earth with metronomic regularity. Some pulsars rotate hundreds of times per second, their stability rivaling atomic clocks. When astronomers detected the first binary pulsar in 1974, its subtle orbital decay matched Einstein's predictions of gravitational waves perfectly, offering the first indirect proof of these spacetime ripples decades before LIGO direct detection. Pulsars don't just tick, they're cosmic laboratories, testing the laws of physics under conditions we could never replicate on Earth. But radio astronomy's grandest revelation is far quieter: the cosmic microwave background, the afterglow of the Big Bang. This faint static, discovered when two Bell Labs engineers stumbled upon persistent noise in their radio antenna in 1965, is the oldest light in the universe, stretched from visible heat into microwaves over 13 billion years. It's a snapshot of the cosmos at 380,000 years old, its tiny temperature fluctuations seeding all future structure. Modern telescopes like Planck have mapped these variations with exquisite detail, revealing the infant universe's density wrinkles, the blueprints for galaxies, clusters, and the vast cosmic web. What's astonishing is how these microwave whispers connect to radio's other discoveries. The same hydrogen gas that emits the 21-centimeter line today was once part of that primordial soup. The pulsar's precise beats trace the aftermath of stellar explosions that enriched space with heavy elements and ALMA molecular clouds. They're the latest chapter in a story that began with those microwave ripples. The invisible spectrum doesn't just show us disjointed pieces of the universe, it weaves them into a single, breathtaking narrative, from the Big Bang's echo to the birth of new stars. Imagine holding a photograph of yourself as a newborn, fuzzy, indistinct, but undeniably you. That's exactly what the cosmic microwave background is for the universe, a baby picture taken when the cosmos was just 380,000 years old. This faint glow, discovered by accident in 1965, is the oldest light we can see, stretched from the heat of creation into microwaves by 13.8 billion years of cosmic expansion. It's not just a relic, it's a time machine showing us the universe before the first stars flickered on, when everything was a scorching soup of particles and light. The magic of the CMB lies in its imperfections. If the early universe had been perfectly smooth, we wouldn't exist. Instead, satellites like WMAP and Planck have mapped tiny temperature variations, fluctuations no larger than 1 part in 100,000. These microscopic wrinkles in spacetime were the seeds of everything, the gravitational wells where matter pooled, forming the first galaxies, clusters, and the vast cosmic web we see today. It's like watching the first raindrops hit a pond, knowing they'll eventually create ripples big enough to move ships. What's astonishing is how much these microwave whispers tell us. By measuring the CMB's patterns, astronomers have calculated the universe's age, composition, and even its fate. Those faint hot and cold spots reveal that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. The rest, dark matter's invisible scaffolding and dark energy's mysterious push, both detectable only by their gravitational fingerprints on this primordial light. But the CMB isn't just a snapshot, it's a puzzle with missing pieces. Some large-scale patterns in the microwave background don't quite match our theories, hinting at physics we don't yet understand. Could these anomalies be traces of other universes, relics from before the Big Bang, or something even stranger? The invisible spectrum keeps its secrets close, but every new generation of telescopes brings us closer to reading the universe's hidden diary. And speaking of secrets, what about the 85% of the universe that doesn't glow at all? Dark matter and dark energy don't emit light, yet their presence warps the cosmos in ways the CMB helps us measure. It's like hearing the footsteps of an invisible dancer. You can't see them, but you know they're there by the way the stage shakes. As we peel back layer after layer of the invisible spectrum, who knows what other ghosts of creation we'll find hiding in the static? Here's a universe-sized elephant in the room. 85% of all matter doesn't interact with light at all. You could stare straight through a chunk of dark matter and never know it was there because, unlike stars, gas, or planets, this mysterious substance doesn't absorb, reflect, or emit any electromagnetic radiation. Yet its gravitational grip is unmistakable. Galaxies spin so fast they should fling themselves apart, but something invisible holds them together. Light bends around seemingly empty patches of space as if tugged by hidden mass. The cosmos is teeming with matter we can't see, and its fingerprints are everywhere once you know where to look. Take galaxy rotation curves, a cosmic detective story written in starlight. When astronomers measured how fast stars orbit galactic centers, they expected speeds to drop off farther from the core, like planets slowing down as they move outward from the sun. Instead, stars at a galaxy's edge whip around just as fast as those near the middle. The only explanation, an enormous halo of invisible matter enveloping each galaxy, its gravity keeping stars from flying off into the void. This missing mass isn't just a small oversight, it outweighs visible matter 5 to 1. Then there's gravitational lensing, nature's ultimate sleight of hand. When light from distant galaxies warps around massive objects, it creates stretched or duplicated images, like looking through a funhouse mirror. But often, the distortion points to far more mass than the visible galaxy cluster causing it. Some of the most dramatic examples reveal perfect Einstein rings, halos of light bent into circles by dark matter's unseen bulk. It's as if space itself is haunted by ghostly matter, bending reality without ever showing its face. So what is this shadowy cosmic scaffold? Physicists have two leading suspects: WIMP, weakly interacting massive particles, are heavy, slow-moving hypothetical particles that barely touch normal matter except through gravity. Underground labs like Italy's Gran Sasso mine hunt for WIMP using vats of liquid xenon, waiting for the rare bump when one collides with an atom. Then there are actions, ultralight particles born from quantum field theory, which might convert to detectable photons in strong magnetic fields. Experiments like ADMCS in Washington state tune giant radio cavities like cosmic AM receivers, searching for actions' faint whispers. But dark matter isn't the only invisible player reshaping the cosmos. In the late 1990s, astronomers measuring distant supernovas made a chilling discovery. The universe isn't just expanding, it's accelerating. Something is stretching space itself faster over time, and we've dubbed this unknown force dark energy. Unlike dark matter's gravitational pull, dark energy seems to push, accounting for nearly 70% of the universe's total energy. Together, dark matter and dark energy form a 95% cosmic blind spot, reminding us just how much of the universe's story remains hidden in the shadows. Here's the twist: dark matter might not be completely dark after all. Some theories suggest certain particles could decay into faint X-rays or gamma rays. Telescopes like Chandra and Fermi scour the sky for unexplained energy spikes near galaxy clusters or dwarf galaxies, places where dark matter should densely congregate. Even neutrinos, those nearly massless ghost particles streaming through your body right now, were once thought to be dark matter candidates. While too light to explain all of it, they prove nature loves hiding matter in plain sight. The hunt for dark matter isn't just about filling a gap in our equations, it's about rewriting the cosmic origin story. Simulations show dark matter's gravity sculpted the first galaxies, its invisible tendrils guiding gas into the webs where stars ignited. Without it, the universe would look utterly different, and that's the humbling truth. We're like actors on a stage, oblivious to the wires holding up the set. Yet every unexplained lensing event, every too-fast galaxy, every peculiar energy spike is a clue. The invisible spectrum isn't just about light we can't see, it's about matter we can't touch, forces we don't feel, and a cosmos far stranger than our senses ever hinted. In the late 1990s, astronomers pointed telescopes at distant supernova, expecting to measure how much the universe's expansion was slowing down, and got the shock of their careers. Instead of decelerating under gravity's pull, these exploding stars appeared dimmer than they should have been, as if space itself was stretching faster over time. It was like tossing a ball in the air and watching it rocket away instead of falling back. The culprit, a mysterious repulsive force we now call dark energy, making up 68% of the cosmos and flinging galaxies apart at ever-increasing speeds. The real breakthrough came from combining observations across the spectrum. Visible light revealed the supernova's telltale signatures, while infrared measurements pierced through cosmic dust to confirm their distances. Together, they painted an irrefutable picture. The universe isn't just expanding, it's accelerating, as if some invisible foot is pressing harder on the cosmic gas pedal with each passing moment. This discovery flipped cosmology on its head, earning researchers the Nobel Prize in 2011, and leaving everyone else scrambling to explain how empty space could possess such staggering energy. The leading theory, vacuum energy, a sort of anti-gravity woven into spacetime itself. Quantum physics suggests that even a perfect vacuum bubbles with fleeting particles popping in and out of existence, generating a repulsive force. Trouble is, calculations predict this energy should be 10 to the power of 120 times stronger than what we observe. It's the worst mismatch in science, like predicting a candle's glow and measuring the brightness of a supernova instead. Some theorists tweak Einstein's equations, proposing modified gravity theories where the laws themselves change over cosmic distances. Others imagine dark energy as a dynamic field, evolving over time like an invisible fifth force. Enter Euclid, the European Space Agency's dark energy detective. Launching soon, this space telescope will map billions of galaxies across 10 billion light-years, measuring how dark energy has shaped cosmic structures over time. By combining visible and infrared imaging, Euclid will trace the subtle warping of spacetime around galaxy clusters, a phenomenon called weak gravitational lensing, to weigh dark matter's pull against dark energy's push. It's not alone. The Vera Rubin Observatory's 3200 megapixel camera will scan the sky nightly, while NASA's and Nancy Grace Roman Space Telescope will hunt for distant supernova. Together, they'll test whether dark energy's strength has changed across cosmic epochs, potentially revealing if it's a constant vacuum property or something far stranger. The key to solving this puzzle lies in multi-wavelength astronomy. Just as a doctor uses X-rays, MRI, and ultrasounds to see different layers of the human body, astronomers combine spectra to decode the universe's hidden anatomy. Radio telescopes map dark matter's distribution via 21-centimeter hydrogen lines. X-ray observatories trace hot gas in galaxy clusters, weighing their total mass. Meanwhile, gamma-ray detectors hunt for exotic particle decays that might betray dark energy's origins. Each wavelength tells a different part of the story, and only by stitching them together can we glimpse the full picture. Perhaps the most mind-bending possibility is that dark energy isn't a thing at all, but a sign that our understanding of gravity breaks down on cosmic scales. Just as Newton's laws needed revising for extreme speeds, hello, Einstein, maybe general relativity needs tweaking for vast distances. Some theories propose extra-spatial dimensions curled up tightly, influencing gravity in ways we can't yet perceive. Others suggest dark energy is an illusion, a side effect of living in a rare, underdense region of an infinite multiverse. Whatever the answer, one thing's clear: the invisible spectrum isn't just revealing hidden objects, it's exposing fundamental gaps in our grasp of reality itself. From supernovas' infrared whispers to gamma rays' violent bursts, every wavelength offers another piece of this cosmic jigsaw. And with next-generation telescopes set to peel back even more layers, we might soon find that dark energy isn't the end of the story, but the gateway to something even more profound. Listening to the universe with only one wavelength is like trying to appreciate a symphony by hearing nothing but the violin section. You'll catch the melody, but miss the richness of the brass, the depth of the cellos, the rhythm of the percussion. Astronomy works the same way. A black hole observed solely in X-rays might look like a voracious monster, gulping down superheated gas. Switch to radio waves, and suddenly you see colossal jets of particles shooting out at nearly light speed. Add infrared, and the dust clouds hiding its feeding frenzy come into focus. Only by combining these perspectives do we get the full score of cosmic activity, and few objects demonstrate this better than Centaurus A, a galaxy that's been studied across every wavelength we've got. At first glance in visible light, Centaurus A looks like a messy collision, a spiral galaxy tangled with an elliptical one, wrapped in bizarre dust lanes. But point an X-ray telescope at it, and the scene erupts. Twin jets blast from its supermassive black hole, heating surrounding gas to millions of degrees. These jets stretch over 1 million light-years, visible only in radio wavelengths, where they glow as some of the largest structures in the universe. Meanwhile, infrared observations cut through the dust, revealing rings of star formation triggered by the galactic smash-up. Each wavelength peels back another layer, showing how the black hole's tantrums shape its entire galaxy. This multi-wavelength approach has revolutionized our understanding of cosmic violence. Take galaxy collisions. In visible light, they might look like two glowing blobs merging. Add radio data, and you'll often catch shock waves from supernovas or the hum of newly formed black holes. Infrared reveals hidden starbursts, where the collision compressed gas clouds into a frenzy of star birth. Even gamma rays can expose the aftermath, as particles accelerated to extreme energies create telltale flashes. It's not just about seeing more details. It's about seeing connections, how energy flows from black holes to gas clouds to newborn stars in one vast cosmic circuit. The tools making this possible are nothing short of engineering marvels. Space telescopes like Hubble, Chandra, and Webb each specialize in different wavelengths, working in concert like an orchestra of observatories. Hubble's sharp, visible light vision captures galaxies' delicate structures, while Chandra's X-ray eyes expose the scorching gas around black holes. The James Webb Space Telescope, tuned to infrared, peers through dust to spot the universe's first galaxies. Down on Earth, radio dishes like ULMA listen to the cold molecular clouds where stars are born. Together, they transform disjointed snapshots into a moving picture, revealing how celestial objects evolve over time. Consider how this played out with the black hole at our galaxy's core. For years, astronomers tracked stars whipping around an invisible point in visible light, hinting at something massive. X-rays then spotted flares as matter fell into the black hole's grip. Finally, radio telescopes linked dishes across the planet to snap the first direct image of its shadow, a dark silhouette against glowing gas, exactly as Einstein's equations predicted. No single telescope could have told this story alone. It took the combined power of multiple wavelengths to go from suspicion to certainty, from theory to breathtaking reality. The future of multi-wavelength astronomy looks even brighter. Upcoming missions like the European Space Agency's Athena and X-ray Observatory will map hot gas structures across the universe. The Square Kilometre Array, a radio telescope network spanning continents, will detect hydrogen gas from the cosmic dawn, and NASA Spherix will scan the entire sky in infrared, hunting for clues about the universe's expansion. Each new instrument adds another section to our cosmic orchestra, letting us hear the universe's symphony in ever greater depth. What began as separate snapshots, radio maps, X-ray flares, optical images, is becoming a unified movie of an evolving, dynamic cosmos, where every wavelength reveals a new plot twist in the grandest story there is. Gaze upward on a clear night, and Earth's atmosphere seems perfectly transparent, but to astronomers, it's like trying to study the stars through a frosted window. Our air distorts light, absorbs crucial wavelengths, and scatters the faintest cosmic whispers before they ever reach the ground. That's why we've launched our eyes beyond the atmosphere, building telescopes so precise they could spot a candle flame on the moon. Hubble, Chandra, Webb, these aren't just machines, they're time machines, each tuned to a different slice of the invisible spectrum, revealing layers of the universe no human eye could ever see. Take Hubble, our most iconic cosmic photographer. Orbiting since 1990, it's captured galaxies colliding, stars being born, and planets forming in dusty disks, all in crisp, visible, and ultraviolet light. Without atmospheric turbulence blurring its view, Hubble's images are up to 10 times sharper than anything from Earth. But Hubble's just one specialist in a larger team. Point Chandra at the same patch of sky, and the serene visible light scene erupts into an X-ray inferno, black holes devouring stars, neutron stars spinning at dizzying speeds, gas heated to millions of degrees in galaxy clusters. Meanwhile, the James Webb Space Telescope peers through cosmic dust in infrared, spotting the universe's first galaxies as they looked over 13 billion years ago. Building these observatories is like engineering a Swiss watch the size of a school bus, one that must survive rocket launches, extreme temperature swings, and the vacuum of space. Hubble's infamous blurry vision at launch required a daring shuttle repair mission to fix. Webb's 18 hexagonal mirrors had to unfold with nanometer precision in frigid conditions, its sun shield as thin as a human hair yet large enough to block a tennis court's worth of solar heat. And Chandra, its grazing incidence mirrors focus X-rays like skipping stones across a pond, a feat impossible with conventional lenses. Why go through all this trouble? Because space offers what Earth never can: silence. No twinkling stars, no water vapor absorbing infrared, no daytime to interrupt observations. A single Hubble deep field image, captured over 11 days, revealed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. Webb's infrared vision has spotted galaxies so mature in the early universe, they're rewriting cosmic timelines, and Chandra's X-ray eyes have traced dark matter's distribution by watching how its gravity bends high-energy light. The next generation of space telescopes will push boundaries even further. NASA's Nancy Grace Roman telescope will map dark energy's expansion of the universe with a field of view 100 times larger than Hubble's. ESA's Athena X-ray Observatory will study supermassive black holes with unprecedented precision, and projects like the Habitable Worlds Observatory aim to directly image Earth like exoplanets, searching for signs of life. These missions won't just add new chapters to our cosmic story, they'll rewrite entire sections we thought we understood. What's astonishing isn't just what these telescopes reveal, but how they complement each other. A galaxy in Hubble's visible light might look serene, while Chandra catches its black hole spewing jets of particles, and Webb uncovers hidden star formation in its dust lanes. Together, they transform flat snapshots into multidimensional portraits, proving that to truly see the universe, you need more than eyes. You need a symphony of light, each instrument playing its part across the electromagnetic spectrum. The next decade of astronomy will crack open cosmic mysteries we've barely begun to fathom, thanks to a new wave of telescopes designed to read the universe's hidden language. At the forefront is NASA's Nancy Grace Roman Space Telescope, launching around 2027, armed with a camera so powerful it could spot a penny from 15,000 miles away. But Roman's real superpower lies in its infrared vision, which will map dark energy's fingerprints across billions of galaxies. By measuring how clusters of galaxies warp spacetime over cosmic epochs, Roman will test whether dark energy evolves, a discovery that could rewrite physics textbooks. It'll also hunt for rogue planets drifting between stars, worlds so cold they emit only faint infrared glows, invisible to other telescopes. Then there's LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the 2030s. Instead of light, LISA will detect gravitational waves, ripples in spacetime caused by collisions between supermassive black holes. These waves stretch and compress space itself as they pass, and LISA trio of spacecraft will measure these distortions with lasers accurate to a fraction of an atom's width. Imagine hearing the universe's bass notes for the first time, the mergers of black holes so massive they shake the fabric of reality, events no telescope could ever see but LISA will feel. Together, Roman and LISA will explore the invisible universe in ways that complement each other perfectly, one mapping dark energy's push, the other tracing the black hole crashes it enables. Ground-based telescopes aren't being left behind. The extremely large telescope, rising in Chile's Atacama Desert, will gather more light than all of history's largest telescopes combined when it opens in 2028. Its 39-meter mirror, half the length of a soccer field, we'll analyze exoplanet atmospheres in infrared, hunting for biosignatures like oxygen and methane. Picture this: starlight filtering through an alien world's air, absorbed at specific wavelengths by molecules we associate with life. The ELT could spot these chemical fingerprints on planets dozens of light years away, turning speculation about extraterrestrial life into hard data. What's thrilling is how accessible invisible astronomy has become. Amateurs can now attach infrared filters to backyard telescopes, capturing heat signatures from Jupiter's storms or the Moon's ancient lava flows. Radio enthusiasts build DWI antennas to listen for hydrogen emissions from the Milky Way, while citizen science projects like Zooniverse let anyone classify galaxies in infrared surveys. The barrier between professional and amateur astronomy is dissolving because the universe's secrets don't belong to any one group. They're there for anyone curious enough to look beyond the visible, to listen for the whispers of light we can't see but know are telling extraordinary stories. The future of astronomy isn't just about bigger telescopes, it's about sharper questions. Could next-gen instruments spot industrial pollutants in exoplanet atmospheres, hinting at alien civilizations? Will gravitational waves reveal hidden dimensions? Every time we've expanded our view across the electromagnetic spectrum, we've uncovered phenomena that defied expectations. The next breakthroughs won't just fill gaps in our knowledge, they'll tear open entirely new chapters, proving once again that the universe is stranger, more violent, and more wondrous than our limited senses ever suggested. And the best part, you don't need a PhD to be part of the discovery. The invisible spectrum is waiting, and it speaks to anyone who learns how to listen. You don't need a $1 million telescope to explore the invisible universe. Some of its greatest discoveries start in backyards and basements. Citizen scientists armed with nothing more than curiosity and a laptop have helped classify thousands of galaxies in infrared surveys, spotting oddities professional astronomers might have missed. Projects like Zooniverse's Galaxy Zoo let anyone scroll through images from NAS, a WISE telescope, tagging strange shapes or unusual dust patterns that could lead to breakthroughs. One volunteer even discovered an entirely new type of galaxy, dubbed green peas, for their vivid hue in infrared, proving you don't need a PhD to contribute to cosmic knowledge. For those who want hands-on experience, affordable tools open surprising windows into the unseen. A modified DSLR camera with its infrared filter removed can capture near-infrared light, revealing hidden details in everyday scenes like how tree leaves glow brighter than their surroundings due to chlorophyll's unique infrared signature. Amateur astronomers use these cameras to photograph the moon in near-infrared, highlighting mineral variations invisible to the naked eye. And with radio kits as simple as a USB dongle and a homemade antenna, enthusiasts can tune into the 21-centimeter hydrogen line, mapping the Milky Way's spiral arms from their driveway. The best part, you can explore like a pro without buying any gear. NASA and ESA release raw data from telescopes like Hubble, Webb, and Chandra to the public, letting anyone process images of distant nebulas or black hole jets. Online platforms like the Micro Observatory Robotic Telescope Network even let you control real telescopes remotely, snapping your own infrared shots of star clusters or galaxies. It's a golden age for amateur science, where a teenager with a laptop can analyze the same cosmic data as a seasoned astronomer. But beyond the thrill of discovery, these invisible wavelengths invite deeper questions about perception and reality. Every time we've expanded our view of the spectrum from Galileo's first telescope to Webb's infrared eyes, we've been humbled by how much we've missed. The universe isn't just stranger than we imagined. It's stranger than we can imagine, with entire layers of reality hidden until we build the right tools to reveal them. That's the real lesson of the invisible spectrum. Our senses show us only a sliver of existence, and the truth is always richer, wilder, and more beautiful than we've dared to assume. Every major leap in astronomy has shattered our cosmic ego. First, we learned Earth wasn't the center of the universe, just a speck orbiting an average star. Then we discovered that star was one of billions in a galaxy, itself one of countless others. Now, the invisible spectrum delivers another humbling truth. The universe we thought we knew is just a tiny fraction of what's really out there. It's like spending your whole life in a dimly lit room, only to suddenly flip on the lights and realize you've been missing an entire mansion. Consider how this mirrors history's great scientific wake-up calls. When Galileo pointed his telescope at Jupiter in 1610 and spotted moons orbiting another planet, it proved not everything revolved around Earth, a revelation so threatening it got him imprisoned. Today, infrared and X-ray telescopes are our modern Galilean instruments, revealing celestial phenomena that defy our assumptions. Supermassive black holes, invisible to the naked eye, govern entire galaxies. The cosmic microwave background, a faint radio whisper, carries echoes of the Big Bang itself. These discoveries don't just add to our knowledge, they redefine our understanding of reality, showing us how much exists beyond human perception. Culturally, this shift is profound. For centuries, we've equated seeing with knowing, but invisible light forces us to confront how limited our senses are. The night sky isn't a static painting. It's a dynamic, multi-wavelength spectacle where most of the action happens offstage. Artists and writers have begun embracing this. Modern planetarium shows blend visible and infrared visuals, while sci-fi increasingly depicts aliens sensing entirely different spectra. Even language adapts. Phrases like X-ray vision and heat vision have entered our lexicon, reflecting how these once mythical abilities are now tools in our scientific toolkit. The practical spin-offs are just as revolutionary. Infrared cameras spot heat leaks in homes, helping slash energy bills. Ultraviolet light sterilizes hospitals, saving lives. X-ray scanners at airports detect threats invisible to the naked eye. Even your smartphone's facial recognition uses infrared dots to map your features in the dark. These technologies all trace back to astronomers' quest to decode the cosmos, proof that exploring the invisible doesn't just satisfy curiosity, it transforms daily life. Perhaps the most poetic application lies in medicine, where we've turned the cosmos' hidden light into life-saving tools. MRI machines, descendants of radio astronomy, peer inside the human body with the same precision astronomers used to study distant galaxies. PET scans detect gamma rays from injected tracers, revealing cancer cells like celestial gamma ray bursts pinpoint stellar explosions. It's a beautiful symmetry. The same wavelengths that unveil the universe's secrets also help heal us, bridging the vastness of space with the intimacy of our own biology. This convergence of cosmic exploration and earthly innovation hints at a deeper truth. Every time we push the boundaries of what we can perceive, whether with telescopes or microscopes, we don't just discover new phenomena. We rediscover ourselves, redefining what it means to be human in an ever-expanding tapestry of light and shadow. The invisible spectrum isn't just showing us the universe, it's teaching us how to see. The same invisible light that reveals black holes and newborn stars also saves lives here on Earth every single day. Take X-rays, those high-energy photons screaming from supernova remnants and black hole jets. They're the very same wavelengths doctors used to peer inside your body without making a single incision. When Wilhelm Röntgen discovered X-rays in 1895, he had no idea he'd unlocked a tool that would revolutionize medicine. Today, a broken bone or a suspicious shadow on a lung can be spotted in minutes thanks to technology born from cosmic curiosity. Even modern CT scans, which build 3D images from X-ray slices, trace their origins to astronomical techniques developed to map the structures of distant galaxies. It's a perfect loop. The universe taught us to see through flesh, and now we use that knowledge to heal. Then there's ultraviolet light, the same searing radiation that exposes the atmospheres of distant stars also keeps our drinking water safe. UV water purifiers blast harmful bacteria with wavelengths just shy of X-rays, scrambling their DNA without chemicals. This isn't some futuristic tech. It's in municipal plants and even backpacking filters, all thanks to astronomers studying how UV light interacts with matter. The connection goes deeper. The ozone layer that protects us from the sun's harshest UV rays was first understood by measuring how starlight gets absorbed as it passes through Earth's atmosphere. Space science didn't just explain the sky, it helped safeguard the ground beneath our feet. Infrared's journey from cosmic tool to everyday essential might be the most surprising. Developed to study cool stars and dust-shrouded galaxies, infrared sensors now power everything from night vision goggles to touchless thermometers. Firefighters use them to see through smoke, farmers monitor crop health from drones, and your smartphone's Face ID relies on infrared dots to recognize you in total darkness. Even the thermal imaging cameras that spotted heat leaks in homes during the energy crisis owe their existence to space telescopes like Spitzer and Webb. The invisible warmth we once thought only stars could emit now helps us navigate, innovate, and survive. But here's the thrilling part: we've only scratched the surface. Astronomers are now experimenting with terahertz radiation, a weird middle ground between infrared and microwaves, to peer through comet ice in deep space. Down here, that same technology could revolutionize airport security, spotting concealed explosives without invasive searches. Gamma-ray detectors designed to catch the universe's most violent explosions are being adapted to hunt for smuggled nuclear materials. And the quantum sensors being developed to detect dark matter, they might one day map the human brain with unprecedented precision. So the next time you get an X-ray or drink purified water, remember, you're touching the cosmos. The invisible light that sculpts galaxies and births stars also heals, protects, and connects us. And if history's any guide, the next great breakthrough won't come from looking harder, but from learning to see differently through wavelengths we've yet to fully explore. After all, every time we've expanded our view across the spectrum, we've uncovered wonders we never knew existed. Who's to say what's still hiding just beyond the edge of our perception? Even as we decode the universe's hidden wavelengths, some of its most electrifying mysteries refuse to reveal their secrets. Take fast radio bursts, those bizarre, millisecond-long blasts of radio waves that pour as much energy as the sun emits in 3 days. First detected in 2007, these cosmic firecrackers arrive without warning, some from galaxies billions of light years away. Are they the death cries of collapsing neutron stars? The aftermath of black hole mergers, or could they be, as some daring theories suggest, evidence of advanced alien propulsion systems? The truth is, we still don't know. What makes these bursts even stranger is that some repeat randomly, while others vanish after a single pulse, as if the universe is teasing us with a radio code we can't crack. Then there's dark matter's stubborn silence. After decades of hunting, we've mapped its gravitational fingerprints everywhere, from the way galaxies spin to how light bends around galaxy clusters, yet we still can't say what it actually is. Underground labs have waited in vain for dark matter particles to bump into atomic nuclei. Space telescopes have scanned for gamma-ray flashes that might signal their decay. Even particle colliders like the Large Hadron Collider have come up empty. The harder we look, the more elusive dark matter becomes, almost as if it's playing by rules we haven't discovered yet. And what about the universe's most baffling energy budget? Dark energy's repulsive force, driving cosmic expansion to accelerate, makes up 68% of the universe's total energy. But here's the kicker. When we calculate how much energy empty space should have based on quantum physics, the numbers are off by a factor of 10 to the power of 120. That's like predicting a candle's glow and measuring the brightness of a billion supernovas instead. Either we're missing something fundamental about vacuum energy, or there's a cosmic sleight of hand we haven't spotted. Even the cosmic microwave background, that pristine baby picture of the universe, hides anomalies. Large-scale patterns in its temperature fluctuations don't quite match our models. Could these be scars from a violent pre-Big Bang era, evidence of parallel universes bumping against ours, or just statistical flukes? Every time we solve one layer of the CMB's mysteries, another pops up, like peeling an infinite onion. The beauty of these puzzles is how each solved riddle births new ones. Take gravitational waves. After LIGO Nobel Prize-winning detection in 2015, we thought we'd unlocked a new window on black holes. Then we caught waves from neutron star collisions and realized they were forging gold and platinum in their wake. Now, astronomers are hunting for intermediate mass black hole mergers, cosmic strings, or even echoes from the Big Bang itself. The invisible spectrum doesn't just answer questions, it rewrites them in real time. Want to join the detective work? You don't need a PhD to track breakthroughs. NASA Chandra X-ray Center and ESA's Webb Telescope teams regularly post raw data for public analysis. Podcasts like the Supermassive Podcast break down new discoveries weekly, while projects like Zooniverse let you classify weird radio signals from your couch. Science is a team sport, and the next big reveal could come from anywhere, maybe even from you hitting pause on this video to dive down a cosmic rabbit hole of your own. Keeping up with the latest cosmic revelations doesn't require a fancy degree, just curiosity and the right tools. NAS, a website, is your front row ticket to the universe's greatest hits, packed with real-time updates from telescopes like Webb and Chandra. Their astronomy picture of the day archive alone is a treasure trove, blending jaw-dropping visuals with bite-sized explanations that turn complex discoveries into aha moments. For on-the-go learning, podcasts like Star Talk or the Supermassive Podcast break down breakthroughs over your morning coffee, often featuring the very scientists behind the research. And if you crave the nitty-gritty, open-access journals like the Astrophysical Journal let us publish cutting-edge findings for free. No paywall, just pure cosmic wonder. But astronomy isn't a solo sport. Local astronomy clubs offer telescope workshops and star parties where you can glimpse Saturn's rings or distant galaxies alongside seasoned observers. Online forums like Cloudy Nights or Reddit's r/astrophysics buzz with debates about new papers, while platforms like Zooniverse let you sift through real telescope data. You might even spot something professionals missed. The key is to dive in wherever feels fun, whether that's chasing auroras with a camera or geeking out over gamma-ray burst alerts on Twitter. Now let's bust some myths. Invisible light isn't some sci-fi gimmick. It's as natural as sunlight. Take infrared. It's not heat vision cooked up for spy movies. It's how pit vipers hunt and how your TV remote works. X-rays, they don't magically penetrate everything. Lead blocks them cold, which is why dentists drape that heavy vest over you. And no, microwaves from space won't give you superpowers or cancer. The cosmos bathes us in these wavelengths daily, harmlessly and invisibly, like a symphony playing just outside our hearing range. The wildest myth: that invisible astronomy is cheating because we can't see it naturally. Tell that to the bees navigating by ultraviolet patterns on flowers, or the mantis shrimp spotting cancer cells with polarized vision. Our eyes evolved to spot ripe fruit and predators, not black holes. Every time we've expanded our sensory toolkit, from microscopes to radio antennas, we've uncovered layers of reality that were there all along, waiting for us to look deeper. The universe isn't hiding its secrets, it's just waiting for us to ask better questions. Let's set the record straight about invisible light because pop culture has spun some wild tales. Take infrared, often reduced to heat vision in movies. Sure, it detects warmth, but that's like calling a smartphone a flashlight. Infrared astronomy reveals cosmic dust clouds, distant galaxies, and even the chemical fingerprints of alien atmospheres. Your TV remote uses infrared too, hardly the stuff of superhero gadgets. Then there's X-rays, vilified as universally dangerous. Truth is, the dose makes the poison. A dental X-ray delivers less radiation than a cross-country flight, and medical imaging saves millions yearly by spotting tumors and fractures. It's like fearing water because tsunamis exist. Context is everything. Gamma rays get the worst comic book treatment, often portrayed as green ooze that turns scientists into hulks. Reality, these are photons, not magic potions. Yes, a gamma ray burst could sterilize a planet, but Earth's atmosphere shields us from most cosmic sources. Meanwhile, doctors harness controlled gamma rays to zap cancer cells with precision. The real superpower here, science, not sci-fi. Another myth, that invisible means undetectable. Tell that to honeybees, which see ultraviolet patterns on flowers guiding them to nectar, or pit vipers hunting prey via infrared pits. Our eyes are the odd ones out, limited to a narrow slit of the spectrum. Upgrade your perspective, and suddenly, invisible becomes a quirk of biology, not a cosmic secret. Now, here's where AI enters the spotlight. With telescopes drowning in petabytes of multi-wavelength data, scientists are turning to machine learning to spot patterns no human could catch. Algorithms sift through radio static to find distant pulsars, classify galaxy shapes in infrared surveys, and even predict solar flares by analyzing ultraviolet bursts. It's not replacing astronomers, it's amplifying them, like giving a detective a fingerprint database instead of a magnifying glass. The takeaway, invisible light isn't mysterious or magical, it's just physics we've learned to decode. And with AI joining the hunt, we're poised to crack even more of the universe's hidden language. Modern astronomy faces a data deluge so vast it would take a human centuries to sift through. Enter artificial intelligence, the unsung hero decoding the invisible universe. Every night, telescopes worldwide capture petabytes of images across the electromagnetic spectrum, from radio whispers to gamma-ray screams. Machine learning algorithms now scan this flood of data with superhuman precision, spotting cosmic oddities that would slip past even the most eagle-eyed astronomer. Take gravitational lenses, those natural telescopes where massive galaxies bend light from objects behind them. AI trained on millions of simulated lenses can pick out these rare distortions in seconds, revealing hidden galaxies billions of light years away that traditional methods might miss. One groundbreaking project uses neural networks to predict stellar explosions before they happen. By analyzing subtle changes in a star's infrared or ultraviolet emissions, algorithms can flag potential supernova days before they visibly erupt. It's like having a cosmic early warning system, giving astronomers precious time to point telescopes at the exact right patch of sky. Other AI tools map dark matter's invisible scaffolding by studying how it warps background starlight, a technique called weak gravitational lensing. What once took months of painstaking manual analysis now unfolds in near real time, with machine learning revealing the universe's hidden skeleton at unprecedented scales. But these tools aren't flawless. Bias lurks in the training data. If algorithms learn only from certain types of galaxies or star systems, they might overlook rare or unexpected phenomena. A neural network trained primarily on spiral galaxies could dismiss an odd-shaped dwarf galaxy as noise. That's why astronomers are crowdsourcing help from citizen scientists through projects like Galaxy Zoo, combining human intuition with machine efficiency to cross-check AI's cosmic sensors. The marriage of AI and invisible light astronomy isn't just accelerating discoveries, it's resurrecting forgotten data. Archives overflowing with decades-old radio observations or infrared scans, once too vast to analyze thoroughly, are getting fresh attention. Machine learning recently uncovered hundreds of new pulsars in vintage Arecibo telescope data, proving that old observations can yield new secrets when viewed through the right algorithmic lens. This technological revolution echoes history's great leaps in cosmic understanding. Just as Galileo's telescope revealed Jupiter's moons in 1610, and Hertz's radio detector opened the electromagnetic spectrum in 1887, AI is now cracking open the 21st century's greatest astronomical challenges. The pattern repeats. Each time we invent new ways to perceive the invisible, the universe grows stranger and more wonderful. From X-rays exposing the bones of stars to algorithms spotting dark matter's ghostly fingerprints, every tool expands our vision beyond the limits of biology. The cosmos has always been shouting its secrets across countless wavelengths. We're finally building the ears to listen. In 1800, astronomer William Herschel made a discovery that would forever change how we see the universe by proving there's light we can't see. While measuring the temperature of sunlight split by a prism, he noticed something peculiar. Just beyond the red edge of the visible spectrum, where no color appeared to human eyes, his thermometer spiked. This invisible heat radiation, soon dubbed infrared, was our first clue that the cosmos communicates in wavelengths beyond our biological limits. Herschel's simple experiment cracked open a door to hidden realities, proving the universe was far more expansive than our senses suggested. Fast forward to 1965, when two Bell Labs engineers named Arno Penzias and Robert Wilson stumbled upon an even bigger cosmic secret. While calibrating a sensitive radio antenna, they kept detecting a persistent hiss, a uniform static coming from every direction in space. After eliminating every possible cause, even scraping out pigeon droppings from the antenna, they realized they'd found the afterglow of the Big Bang itself, the cosmic microwave background. That faint radio whisper, traveling for 13.8 billion years, was the smoking gun for the universe's explosive birth, a discovery so monumental it earned them a Nobel Prize. What's striking is how fiercely both breakthroughs were initially met with skepticism. Herschel's peers struggled to accept that invisible light wasn't an oxymoron, while Penzias and Wilson's noise was at first dismissed as mere instrument error. Today, we take these discoveries for granted, but they remind us how scientific revolutions often begin as anomalies that defy convention. Just as Galileo's telescope revealed moons around Jupiter, proving Earth wasn't the center of everything, these invisible wavelengths exposed a universe teeming with activity our eyes were never built to witness. The impact of these revelations can't be overstated. Infrared astronomy alone has unveiled stellar nurseries shrouded in dust, exposed the violent cores of distant galaxies, and even helped identify organic molecules in space, the building blocks of life. Meanwhile, the cosmic microwave background remains our most powerful tool for studying the infant universe. its subtle temperature variations serving as a blueprint for all the galaxies and voids we see today. Each new window into the spectrum didn't just add to our knowledge, it rewrote entire chapters of cosmic history, yet for all our progress, we're still peering through keyholes. Current telescopes can't detect the faintest radio whispers from the universe's first stars, lost in the noise of cosmic expansion. Dark matter remains stubbornly invisible, its presence inferred only by gravity's tug. And while we've built machines to catch gravitational waves, ripples in spacetime itself, we've barely begun to interpret their messages. The lesson from Herschel to Penzias and Wilson holds true. The universe always has deeper layers to reveal, waiting for the next generation of tools and the next curious minds to bring them into focus. For all the invisible light we've learned to capture, vast stretches of the electromagnetic spectrum remain frustratingly out of reach, like a radio tuned between stations, catching only static where cosmic symphonies might be playing. Take the so-called spectral desert between far infrared and radio waves, a wavelength no man's land where conventional detectors go blind. Here lies a realm too long for infrared telescopes to focus on, yet too short for radio dishes to resolve clearly. It's as if nature drew a curtain across this band, hiding processes we can only theorize about, perhaps the slow-motion dance of cold molecular clouds or the faint glow of the universe's very first stars cooling into oblivion. Then there are the cosmic ghosts, ultra-high-energy neutrinos that streak through Earth by the trillions every second, barely interacting with matter. These subatomic phantoms carry messages from the universe's most violent events, black hole eruptions, colliding neutron stars, yet slip through our detectors like moonlight through a sieve. Current observatories like IceCube in Antarctica catch maybe a dozen of these extreme neutrinos per year, leaving us deaf to most of their stories. Imagine trying to reconstruct a Beethoven symphony by hearing only every 100th note. That's the challenge physicists face when piecing together cosmic cataclysms from these elusive particles. The hunt grows even stranger when we enter the realm of pure theory. Action's hypothetical particles that might solve both the dark matter puzzle and a quantum physics conundrum could be streaming through us right now, their faint waves oscillating through magnetic fields. The problem, their signals would be billions of times weaker than even the faintest radio station. Detecting them would require instruments so sensitive they could measure a snowflake's impact on a mountain. Yet labs like the Action Dark Matter experiment are building action radios with superconducting magnets and quantum amplifiers, hoping to tune into this whisper from the dark universe. What makes these gaps thrilling is how they're birthing entirely new branches of astronomy. Just as the first radio telescopes revealed invisible quasars in the 1940s, next-generation detectors might uncover entirely new cosmic phenomena. The proposed Atacama Large Aperture Submillimeter Telescope could bridge the spectral desert with a 50-meter dish on Chile's high plains. Kilometer-scale neutrino detectors under discussion would catch cosmic rays like never before. And quantum sensors chilled to near absolute zero might finally hear action's faint calls. Every blank spot on our wavelength map isn't just a limitation, it's an invitation to invent new ways of seeing. This relentless push beyond vision's limits is rewriting the search for life itself. Astronomers now scrutinize exoplanet atmospheres in infrared for biosignature gases like methane and oxygen, while radio telescopes listen for artificial signals, not just in visible light but across the spectrum. The molecules that make up life absorb and emit specific wavelengths. DNA itself has a faint ultraviolet signature. Future telescopes might spot vegetation red edges on distant worlds, the telltale infrared reflection of photosynthetic plants, or detect industrial pollutants in alien atmospheres through their unique spectral fingerprints. The lesson is clear: life, like the universe itself, doesn't broadcast on a single channel. To find it, we'll need every wavelength we can harness, and the humility to keep building tools for the light we can't yet see. After all, the greatest discoveries often begin where our senses end. The hunt for life beyond Earth isn't just about pointing telescopes at distant stars, it's about learning to read the universe's hidden language. Take infrared light, astronomy's ultimate biosignature detective. When an exoplanet passes in front of its star, starlight filters through its atmosphere, and certain gases leave telltale fingerprints in specific infrared wavelengths. Water vapor absorbs light at 1.9 and 2.7 microns, methane at 3.3 microns, patterns as distinctive as barcodes. The James Webb Space Telescope recently made headlines analyzing the atmosphere of K2-18b, a distant world where infrared spikes hinted at water vapor and even possible dimethyl sulfide, a molecule on Earth produced only by life. It's like smelling a bakery through a closed door. You can't see the bread, but the aroma gives it away. But life isn't just about what's present, it's about what's survivable. Enter ultraviolet light, the universe's great sterilizer. Young stars flare with brutal UV radiation, stripping atmospheres from nearby planets like sandblasters. Earth survived this gauntlet thanks to its magnetic field and ozone layer, but Mars wasn't so lucky. Yet UV isn't all doom and gloom. In Europa's icy crust or Enceladus's subsurface ocean, UV breakdown of surface ice could create oxidants that seep downward, fueling life in the dark. It's a cosmic irony. The same light that can erase life might also set the table for it in unexpected places. Then there's radio astronomy's quiet revolution in the search for intelligence. SETI Allen Telescope Array scans millions of frequencies for unnatural radio spikes, narrowband signals that nature rarely produces. But the real game changer is technosignatures. Broadband leaks from alien civilizations, like the radio chatter Earth's been accidentally broadcasting since the 1930s. Recent surveys even hunt for laser pulses in optical and infrared, reasoning advanced societies might switch to tighter, more efficient beams. The challenge: distinguishing a real hello from pulsars, satellite interference, or even microwave ovens. A lesson learned when one famous signal turned out to be a telescope's lunchroom appliance. All these searches share a common thread: light as a time machine. When Webb detects an exoplanet's atmosphere 50 light-years away, it's seeing that world as it was when disco ruled Earth. A radio signal from 1,000 light-years would reveal a civilization that flourished during our Middle Ages. Even the absence of signals is data, a cosmic fossil record showing how often life might snuff itself out before reaching the stars. Every wavelength becomes a window not just into space, but into time, letting us piece together the universe's greatest story. Are we alone, or is life just waiting for us to tune into the right channel? The answer might lie in wavelengths we've barely explored. Terahertz radiation, sandwiched between infrared and microwaves, could reveal complex organic molecules in planet-forming disks. Quantum sensors might one day detect the faint magnetic fields of exoplanets, hinting at protective shields like Earth's. And as we comb through radio static for alien messages, we're also learning to listen for the hum of megastructures, hypothetical Dyson spheres, or orbital rings that advanced civilizations might build, leaking heat in predictable infrared patterns. The invisible spectrum isn't just a tool for finding life. It's a mirror showing us how much we still don't know about what life could be. Light doesn't just illuminate the cosmos, it carries snapshots of the past. Every time you look at the night sky, you're peering into a time machine where distant objects reveal themselves not as they are today, but as they were when their light began its journey across the void. Take the James Webb Space Telescope's breathtaking deep-field images. Those faint smudges of infrared light aren't just galaxies, they're cosmic postcards from an era when the universe was a mere 5% of its current age. The deeper Webb stares, the further back it sees, capturing photons that have traveled nearly 13 billion years to reach us, emitted when the first stars and galaxies were just beginning to flicker on in the darkness. This time travel trick works because of redshift, the stretching of light waves as the universe expands. Imagine a cosmic ambulance siren racing away from you. Its sound drops in pitch as the sound waves stretch. Light behaves the same way. The farther away a galaxy is, the faster it recedes from us due to cosmic expansion, and the more its light shifts toward longer, redder wavelengths. Some of the most distant galaxies Webb has spotted emit light that started as ultraviolet or visible, but by the time it reaches us, it's been stretched into infrared, like a voice slowed down until it's barely recognizable. This redshift isn't just a curiosity, it's a measuring tape for the universe, letting astronomers calculate not just how far away these objects are, but how long their light has been traveling. But redshift isn't the only clue in this cosmic detective story. Different wavelengths reveal different chapters of a galaxy's life. Visible light shows mature stars, while ultraviolet exposes hot, young stars blazing with energy. Infrared pierces through dust to uncover hidden star formation, and X-rays trace the violent deaths of massive stars or the feeding frenzies of supermassive black holes. By combining these wavelengths, astronomers can piece together a galaxy's entire biography, from its fiery birth in ultraviolet to its quiet middle age in visible light, and even its eventual fade into infrared obscurity as its stars burn out. It's like reconstructing a person's life from childhood photos, newspaper clippings, and retirement letters. Each wavelength adds another page to the story. So what's the oldest light we'll ever see? The cosmic microwave background, that faint radio whisper from 380,000 years after the Big Bang, marks the ultimate limit. Before that, the universe was too hot and dense for light to travel freely, a fog of plasma where photons couldn't escape, but even that boundary might not be absolute. Future telescopes could detect gravitational waves from the universe's first trillionth of a second, or hunt for neutrinos from the Big Bang itself, particles that slipped through the plasma fog long before light could. Every advance in technology peels back another layer of cosmic history, bringing us closer to witnessing the universe's very first moments. Yet the most mind-bending realization isn't just how far back we can see, it's how much we're still missing. For every ancient galaxy Webb spots, countless others have redshifted beyond detectability, their light stretched into wavelengths too long for any current telescope to catch. Others hide behind walls of cosmic dust or are lost in the glare of closer stars. The universe's earliest chapters remain tantalizingly incomplete, like a jigsaw puzzle with half the pieces still in the box. But with each new observatory pushing deeper into the infrared, radio, and beyond, we're inching closer to reading the full story of cosmic dawn, one photon at a time. The cosmic microwave background isn't just a uniform glow. It's a frozen snapshot of the universe's infancy, etched with faint ripples that tell the story of spacetime's violent birth. Those subtle temperature variations, no stronger than 100,000th of a degree, are quantum tremors from the universe's first trillionth of a second, stretched to cosmic scales by inflation's explosive expansion. Imagine tossing a handful of pebbles into a pond. then watching the ripples grow until they span an ocean. That's what inflation did to quantum fluctuations, magnifying them into the galaxy-forming structures we see today. Now, astronomers are hunting for an even more elusive signature in this ancient light, the faint swirls of primordial gravitational waves. These space-time ripples, predicted to have been generated during inflation, would leave a distinctive curling pattern in the CMB's polarization, a cosmic fingerprint called B modes. Detecting them would be like hearing the echo of the Big Bang itself, confirming that gravity, too, has quantum roots. Projects like the Simons Observatory and Lightbird are deploying armies of ultra-sensitive detectors across mountaintops and even balloons, scanning the sky for these whispers from the universe's first moments. The challenge, distinguishing inflation's signal from the clutter of interstellar dust and the Milky Way's magnetic fields, a task requiring measurements precise enough to spot a snowflake's weight on a continent. What makes these ripples so revolutionary is their quantum origin. The CMB's patterns suggest the universe began as a frothing sea of virtual particles popping in and out of existence, their microscopic jitters inflated to macroscopic scales. This means the galaxies we see today, each with billions of stars, might trace back to quantum fluctuations smaller than an atom. It's as if the universe itself emerged from a cosmic roll of quantum dice, freezing chance into structure. This quantum connection ties light's ancient story to its modern mystery, just as the CMB reveals light's particle-like behavior on cosmic scales. Lab experiments with entangled photons showcase its wave-particle duality in action. The same quantum rules that govern photons streaming from your light bulb also shaped the universe's first light, linking the infinitesimal to the infinite. The CMB doesn't just illuminate the past, it whispers that the universe at its core is a quantum tapestry woven from light and space-time, still vibrating with echoes of creation. Light plays a double game with reality. It's both a wave and a particle, a cosmic trick that shapes everything from telescope designs to the phone in your pocket. Photons, those tiny packets of light, can behave like a ripple spreading across a pond one moment and a marble hitting a target the next. This particle-wave duality isn't just a quirky lab observation. It's the reason modern telescopes need completely different detectors for X-rays versus radio waves. An X-ray photon packs enough punch to knock electrons loose from a metal plate, which is how Chandra's detectors spot black holes, while radio telescopes like ALMA catch light behaving as a wave, with antennas tuned to the gentle rise and fall of electromagnetic ripples from cold gas clouds. The quantum weirdness goes deeper. In 2017, scientists performed an experiment that would have baffled Einstein. They used starlight from distant stars to test quantum entanglement. By splitting photons from Vega and Sirius into entangled pairs, they showed that particles could remain mysteriously linked across cosmic distances, instantly mirroring each other's states no matter how far apart. It's as if the universe wired itself with invisible threads connecting every corner of spacetime, a phenomenon now harnessed in quantum encryption, and soon, maybe even quantum internet. You don't need a particle accelerator to witness light's split personality. That LED screen you're staring at, it relies on quantum mechanics. When electrons in the LED drop to a lower energy level, they emit photons, a particle-like process, but the color depends on the wavelength, a wave property. Even sunlight hitting solar panels is a quantum interaction, with photons kicking electrons loose in silicon to generate electricity. But there's a catch to all this light, we're drowning in it. Light pollution doesn't just erase the stars from our skies, it blinds our tools to the universe's hidden wavelengths. City glare scatters infrared radiation, while radio interference from cell towers drowns out faint cosmic signals. Telescopes now flee to deserts and mountaintops, But even space isn't safe. Satellite megaconstellations streak across Hubble and Webb's images, leaving scars of artificial light in data meant to capture the cosmos' oldest whispers. The irony is stark. The same quantum physics that lets us decode the universe also fuels the gadgets that obscure it. As we push to see further into the infrared and radio realms, we're racing against our own glow, a reminder that understanding light's mysteries requires not just better technology, but darker skies. The night sky, once a universal canvas of stars, is fading before our eyes, not from cosmic changes, but from the glow of our own making. Light pollution now bleaches the heavens for 80% of the world's population, with urban skies so bright that the Milky Way has vanished from view. This isn't just about losing a pretty view, it's severing our connection to the cosmos and crippling our ability to study it. Modern observatories, built at great cost on remote mountaintops, now battle against skyglow from cities hundreds of miles away. The faint infrared glow of distant galaxies, drowned out by the orange haze of streetlights, the delicate radio whispers of hydrogen clouds, jammed by the electronic noise of cell towers and Wi-Fi routers. Even space isn't safe. Megaconstellations of satellites streak across telescope exposures like graffiti on a masterpiece, with companies launching tens of thousands more without regard for astronomy's needs. The impact goes beyond professional research. Consider the Hawaiian Islands, where protests halted construction of the 30-meter telescope atop Mauna Kea. While debates centered on cultural sovereignty, few noticed the irony. Even if built, the telescope would fight a losing battle against light pollution from Honolulu's expanding glow over 100 miles away. Or take Chile's Atacama Desert, home to the world's premier observatories. Satellite trails now contaminate 30% of images from the Vera Rubin Observatory's long exposures, turning cosmic data into Swiss cheese. Radio astronomers face an even grimmer scenario. Our planet's electronic smog has become so thick that some frequencies are unusable for science, forcing telescopes to relocate to the far side of the moon in proposed missions like the Lunar Surface Electromagnetics experiment. Hope flickers in places like Namibia's Namib Rand Nature Reserve, where communities have embraced dark sky certification by using shielded, warm-colored LED lights that minimize sky glow. Similar efforts in Arizona's Flagstaff, the world's first international dark sky city, show how thoughtful lighting can preserve both safety and stars. Grassroots movements are pushing for lights out hours during meteor showers or encouraging homeowners to install motion-sensitive fixtures. The fight has reached policy halls too. Spain's Canary Islands now enforce strict lighting ordinances, while the American Astronomical Society pressures SpaceX to darken its Starlink satellites. You don't need to be an astronomer to join this cosmic rescue mission. Simple actions make a difference, swapping porch lights for downward-facing amber LEDs, supporting dark sky legislation, or even just turning off unnecessary outdoor lighting during key astronomical events. Take a moment to step outside tonight. If you can still see the stars, cherish them. If not, imagine explaining to future generations that we once could look up and see the universe before we drowned it in light. The sky belongs to everyone, and its preservation starts with recognizing that every photon wasted upward is a piece of the cosmos we'll never get back. You don't need a multi-million-dollar space telescope to start exploring the invisible spectrum. Your living room is already full of hidden light waiting to be uncovered. Grab a simple glass prism and hold it up to sunlight, and you'll see more than just a rainbow. Tilt it just right, and you'll spot faint infrared warmth beyond the red edge. The same discovery William Herschel made in 1800 with nothing but a thermometer and curiosity. That TV remote collecting dust on your coffee table, Its infrared LED emits light your eyes can't see, but your smartphone camera can. Point the remote at your phone's lens and press any button. Through the screen, you'll catch the LED flashing with an eerie purple glow, a secret handshake between devices that reveals how much of our world communicates in wavelengths just beyond human vision. For stargazers without telescopes, apps like NASA Eyes on the exoplanets or spacecraft AR turn your phone into a portal for invisible astronomy. These tools overlay real-time satellite data onto your camera view, letting you see ultraviolet auroras or infrared storm systems as if your eyes had superpowers. Want to go deeper? Free software like Salsa J lets anyone analyze raw infrared images from the Spitzer Space Telescope, classifying cosmic dust clouds or tracking star formation. No PhD required. Citizen science platforms like Zooniverse even train you to spot anomalies in real telescope data, turning your coffee break into a cosmic discovery session. The economic ripple effects of these invisible wavelengths stretch far beyond astronomy. Infrared sensors derived from space tech now monitor crop health from drones, boosting agricultural yields by pinpointing thirsty or diseased plants before the human eye can spot trouble. Ultraviolet water purifiers, inspired by how interstellar gas absorbs UV light, provide clean drinking water to millions without chemicals. Even the touchscreen you're swiping right now relies on principles borrowed from X-ray astronomy. The same capacitive sensing that measures star emissions now detects your fingertips. Perhaps most surprising is how invisible light fuels entire industries. Fiber optic cables, carrying 99% of the world's internet traffic, use infrared lasers to shuttle data at light speed. Supermarkets track inventory with RFID tags powered by radio waves, while hospitals rely on gamma-ray sterilizers to disinfect surgical tools. The global market for these technologies tops $2 trillion annually, proof that decoding the universe's hidden light doesn't just satisfy curiosity, it builds economies. So the next time you adjust your smart thermostat or video call a friend overseas, remember, you're harnessing the same invisible forces that shape galaxies. The spectrum isn't just out there, it's in your hands, turning everyday moments into windows on the cosmos. The James Webb Space Telescope cost $10 billion over 25 years, a figure that sounds astronomical until you break it down. That's roughly the price of 2 modern aircraft carriers or what the world spends on coffee every 3 weeks. But unlike a warship or a latte, Webb's value can't be measured in simple economics. Its infrared eyes have already revealed galaxies from the cosmic dawn, analyzed exoplanet atmospheres, and sparked innovations from medical imaging to earthquake prediction. The telescope's sunshield technology, designed to block solar heat, now improves insulation in emergency shelters. Its microshutters' tiny windows that select which light reaches the sensors are adapting into precision drug delivery systems for cancer treatment. International partnerships make these mega-projects feasible. Webb was a collaboration between NASA, ESA, and the Canadian Space Agency, spreading costs across continents while pooling engineering talent. Similarly, the upcoming LUVOIR telescope concept involves scientists from 30 nations, each contributing specialized components. This model turns space telescopes into diplomatic tools, fostering cooperation even among geopolitical rivals. Russia supplies critical mirrors for one instrument while Japan develops spectral analyzers, a reminder that the quest to understand the universe transcends earthly conflicts. Private companies are entering this arena too. SpaceX's Falcon Heavy launched NASA Psyche asteroid mission for a fraction of traditional costs, and startups like Astro Digital build affordable telescopes for both science and commerce. These partnerships create a virtuous cycle. Space agencies get cost-effective launches, companies gain prestige and technical expertise, and taxpayers see returns through spin-off technologies. Google's AI algorithms, originally developed to analyze galaxy images, now power everything from language translation to medical diagnostics, yet ethical questions loom. When a single telescope consumes billions, critics argue those funds could combat poverty or climate change. The counterpoint, space exploration has always been a catalyst for broader progress. The Apollo program's computer miniaturization birthed the microchip revolution, while satellite monitoring now tracks deforestation and illegal fishing in real time. Perhaps the real question isn't whether we can afford space telescopes, but whether we can afford not to build them, because history shows that when humanity reaches for the stars, we inevitably lift life on Earth in the process. The next frontier lies in balancing ambition with equity. As billionaire-funded telescopes compete with publicly funded ones, who gets access to the data? Should profit-driven entities control our view of the cosmos? These debates will shape whether space exploration unites or divides us, but one thing's certain: the economic ripple effects of peering into the invisible spectrum will continue transforming our world in ways we're only beginning to imagine. When we point telescopes at the sky, we rarely ask who that data truly belongs to. The light from distant galaxies may have traveled billions of years to reach us, but the right to interpret it often lands in the hands of a privileged few. Consider the controversy over the 30-meter telescope's proposed construction on Mauna Kea, a mountain sacred to native Hawaiians. Astronomers saw an ideal observation site with minimal atmospheric interference. Indigenous communities saw yet another violation of their ancestral lands. This clash isn't just about real estate, it's about who gets to define the value of the cosmos and who bears the cost of exploration. Data ownership raises equally thorny questions. When a space telescope captures an image of a newborn star, who owns that discovery? The funding agency, the scientists who analyzed it, or does it belong to humanity itself? Some institutions still guard datasets like corporate secrets, locking groundbreaking findings behind paywalls for years. Yet projects like the James Webb Space Telescope have embraced open access policies, releasing raw images within hours of capture, allowing amateur astronomers and researchers worldwide to make unexpected discoveries. The difference is stark. One approach treats the universe as a commodity, the other as a shared inheritance. Naming rights reveal another layer of inequality. Telescopes and celestial objects often carry the names of wealthy donors or colonial figures, erasing indigenous sky knowledge in the process. The Andromeda Galaxy, for example, has been known as the Great Cloud in Maori traditions for centuries, yet Western catalogues rarely acknowledge these older, culturally rich designations. Efforts like the International Astronomical Union's Working Group on Star Names aim to rectify this, officially recognizing names from Chinese, Aboriginal, and Polynesian astronomy alongside Greek and Latin conventions. It's a small but vital step toward decolonizing the cosmos. The push for inclusivity extends beyond symbolism. Access to telescope time remains heavily skewed toward elite institutions, with proposals from researchers in developing nations often sidelined due to lack of funding or infrastructure. Initiatives like the Telescope Access Program are bridging this gap, offering grants for astronomers in underrepresented regions to collaborate on major observatories. Meanwhile, citizen science platforms invite the public to classify galaxies or hunt for exoplanets, democratizing discovery in ways that would have been unthinkable a generation ago. Open science isn't just ethical, it's practical. When the Event Horizon Telescope released its first black hole image, it didn't just publish a pretty picture, it shared petabytes of raw data. Within weeks, independent researchers had reprocessed the information, revealing finer details and even questioning initial conclusions. This collaborative model accelerates progress, turning every observer into a potential co-discoverer. The universe doesn't belong to any one nation, corporation, or academic clique. It's a collective resource, and its study should reflect that. As we stand on the brink of even grander observatories, megatelescopes on the moon, gravitational wave detectors in space, we have a choice: replicate old hierarchies or build a more equitable astronomy. The invisible spectrum shouldn't be a privilege for the few, but a dialogue open to all. Because when we limit who gets to study the stars, we don't just silence voices. We blind ourselves to perspectives that might finally help us understand the cosmos in full. The invisible spectrum hasn't just filled gaps in our cosmic knowledge, it's rewritten the story entirely. What began as a curiosity about heat beyond the rainbow has unraveled the universe's deepest secrets. Stars being born in dusty cradles we once thought were voids, black holes shredding matter in X-ray screams, the afterglow of creation itself humming in microwave static. Each wavelength we've learned to read has peeled back another layer of reality, proving the cosmos is far stranger and more dynamic than our ancestors ever dreamed. Infrared revealed the universe's hidden nurseries. Ultraviolet exposed stellar firestorms too violent for human eyes. Gamma rays betrayed collisions so energetic they forged gold in their wake. And radio whispers carried echoes of the Big Bang, a relic so ancient it predates the first stars. But the most humbling lesson isn't what we've discovered, it's how much remains unseen. Dark matter's gravitational fingerprints are everywhere, yet the particles themselves evade capture. Dark energy's repulsive force accelerates cosmic expansion, but we can't explain why empty space holds such power. Even the ordinary matter we know is mostly invisible, with galaxies floating atop oceans of hot gas only detectable in X-rays. The universe, it seems, is a hall of mirrors, showing us reflections while keeping the sources just out of view. This quest to see the unseen is humanity's oldest and most relentless scientific adventure. From Galileo's first telescope to Webb's infrared gaze, every leap in perception has brought new wonders and new questions. The pattern is clear. Each time we invent tools to expand our senses, the cosmos reveals another frontier. Today's children might live to see telescopes that capture terahertz light from the earliest molecules, or neutrino detectors that map black holes in ways light never could. The invisible spectrum isn't a puzzle to solve. It's an endless conversation, with the universe always holding the next revelation just beyond reach. So the next time you step outside on a clear night, remember, the stars above are just the prologue. Behind them stretches a tapestry of hidden light, infrared glow from budding planetary systems, ultraviolet fury from dying stars, radio murmurs from the dawn of time. As Carl Sagan once said, somewhere, something incredible is waiting to be known. That's the true gift of the invisible spectrum, not just the answers it's given us, but the mysteries it insists we keep chasing. The universe is talking. We're only beginning to learn how to listen.